Hello everyone. Thanks for joining the webinar. My name is Lerche. I studied biophysics at the Lomonosov University in Moscow and at the Humboldt University in Berlin. In my academic career, I was interested in membrane transport, cell-cell interaction, and blood rheology. In 1994, I founded my own company, the LUM GmbH. The business idea was to provide accelerated stability testing of suspensions and emulsions by analytical centrifugation. Our first target was to develop an analyzer for blood sedimentation rate determination to overcome the traditional manual erythrocyte sedimentation rate. After 25 years, we have now 7 product lines, intense cooperation with many universities. We serve customers in about 50 countries. 50 employees at the headquarters, LUM Americas, LUM China, LUM Japan, and the biotech spin-off Dr. Lerche KG are working and serving the customers. Let's first have some general remarks regarding particle sizing methods. You know, most methods are using spectroscopic ensemble techniques. This means we are measuring all particles together, and afterwards, the signal is analyzed regarding the different particles. Another method, which is mostly based on sedimentation, is the fractionating method. Here, the system is fractionated by gravity or analytical acceleration, and we have the different fractions, and then we are analyzing all the fractions individually. And the next part is the counting method. Here, the particles are also separated, but they are very distant from each other, so that finally we are measuring each single particle with the instrument. The new instrument, what I like to discuss with you, the LUMiSpoc, is using this technique. We have fluidics, we have optics, we have electronics, and we have the software. Based on hydrodynamic focusing and single particle light scattering, we can count and size any individual particle. What does it mean, hydrodynamic focusing? We know it from the confluence of 2 rivers. If we have 2 rivers which are coming together, then they are not immediately mixing, the streaming from the both rivers, but as you can see, it looks like we have here a wall. If the cross-section is about the same, then the velocity is larger. And exactly this we are using in our flow microcell. We have the small river with the particles, they are flowing here. We have the sheath fluid, which is bringing much more liquid into the cell, which is coming in here. And due to this and the geometrically shaped system, the particles are lined up, and the distance, as you can see, between the different particles becoming larger and larger. We have really single particles in the capillary. And by changing the flow rate of the sheath liquid or the sample flow, we can change the thickness of the streamlines of the streaming sample flow. If we have a very low sheath liquid flow and a high sample flow, we have a larger cross-section. If we have a very low sample flow and a very high sheet flow, then we have a tiny streamline. This can be measured how large is the cross-section experimentally or simulated theoretically. What you can see here, if the ratio is low, we have about 27 micrometer cross-section, and here we have about 5 micrometers. So the measuring volume is very small, and each particle is lined in a very narrow sample stream. Now, how to count? This we are doing by a laser. The laser is focused in this narrow capillary, and of course, if the particles hit the laser beam, then they are starting to scatter the light. We have forward light and we have sideward light. The electronics registers the intensity. If the particle is very far, then we do not have any intensity. If the particle is touching the laser beam, then we are getting some intensity, some scattering. If the particle is moving into the center, then we have a much higher scattering intensity. And finally, if the particles is moving out, then of course the intensity goes again to zero. Each particle generates a light impulse, an event which is counted, and the scattered light intensity quantifies the particle characteristics, let's say the size. Let's come to the summary, to some main technical features of the LUMiSpoc. The most important thing is that we can detect forward and sideward light scatter of single particles, and that we have hydrodynamic focusing, which allows us to go to very high particle concentrations. We have a very good resolution regarding the intensity detection. We have some flexibility regarding the concentration of the particles by adjusting the sheath and the sample flow. And finally, maybe what is very important, it's only necessary to calibrate the system with one reference-sized particles. The quantitative data are that we can measure from about 40 nanometer up to about 8,000 nanometer. It depends, of course, from the particles. We have a minimum resolution of size differences of about 10 nanometers. We have a very fast measurement rate, so we can go up to 10,000 particles per second for the sizing. We have very broad amplification and classification range, and the particles can be classified in 1 million bins. And you can also see that we have the maximum concentration is about 10 to the 9th particle per milliliter, and the minimum concentration about 10 to the 3rd particle per milliliter. We have successfully tested the system for suspensions, for pharmaceutical emulsions, biological objects, CMP slurries, filter media and separation membrane testing, and the quality of particulate dispersions-based products. You can very nicely analyze reference particles and the purity of solutions. I hope that the webinar gave you some insight into the new measurement technique for sizing and counting of nano and microparticles by the LUMiSpoc. I thank you very much for your attendance. If you have any questions, do not hesitate to contact support or have a look at provided internet information. Thank you once more, stay healthy and have a nice day.